Let's talk a little bit now about color temperature and the related concept of white balance. Color temperature is a way of categorizing the color of white light, and white balance is how the camera interprets that number. All right. This is actually a very simple concept. Hot things glow. You've seen examples of this your whole life. Living in Hawaii, maybe you've gotten to see a lava flow. Probably you've cooked popcorn or soup or ramen on an electric stove. And who knows, maybe you've even watched movies where they torture the bad guys using pokers from fireplaces. The concept is always the same. The coil on your stove, the metal coil, the iron poker, the rock, these are not things that emit light. But because they're so very, very hot, they start to glow. They start to emit light. And the hotter they get, the more the character of that light changes. So let's take a minute here and just look at a regular light bulb. This is a 40-watt light bulb. I bought it for about $1 down at the hardware store, and I have it hooked to a household dimmer. So notice that as I barely turn it on, the light is very dim. But not only is it very dim, it's not white. This is a very warm color, right? It's orange. It's barely visible on the screen, but it's definitely a warm tint. As I start to turn the power up, three things are happening at the same time. One is it's getting brighter. The second is that the color is changing, right? It started out kind of orangey, it moved through kind of yellow, and it's heading on up to what you perceive as white. And then the third thing you can't tell from the video, but the light itself is physically getting hotter. If I touched it when it was barely glowing, it was barely warm. Once it's all the way to its full power, it's actually quite hot, and I really don't want to touch it. If you look at this on a graph, and we were to plot it, so our horizontal axis is the colors of the rainbow, red, orange, yellow, green, blue, indigo, violet, right, Roy G. Biv, and the vertical axis is brightness. When something is barely hot enough to glow, it just gives off red light. That's all we can see. There's infrared off to the left there, but our eyes don't work that way. And it's not very bright at all. As it gets hotter, not only does it get brighter, but that color shifts to the right on our chart, right? It's still putting out some red light, but it's beginning to put out more orange light, and you can see that it's getting brighter. And it continues. The more energy we put into it, the more heat we get, the more that curve shifts. Now we have red, orange, and yellow light all mixing together, even a little bit of green. We're starting to see that with our eyeballs as heading towards white light. And we can see that it's getting brighter and brighter. And this continues. There's a point at which we perceive the color as pure white. And you'll see as the temperature increases, the overall brightness increases, and that curve is pushing towards the right-hand side. And if it continues, the light actually starts to appear blue to our eyes. The way our eyes are designed, of course, we evolved for the sunlight. So what we perceive as white light is the color temperature of the sun on a clear day. I've used the word color temperature. Let's imagine now you're a scientist, or maybe you are a scientist, maybe we don't have to imagine, but you want to find a way to measure the color of light, and it needs to be as objective as possible. So you're going to start by having a perfectly black ball. And I mean, this ball is really black. It's so black you almost can't see it. It looks like a hole in the universe. It does not reflect any light whatsoever. If you shine a light on it, it's still just perfectly black. And you're going to take this black ball and you're going to start heating it up. But being a scientist, you're not going to use a temperature scale that most people use. Fahrenheit's not good enough for you. Celsius is not good enough for you. You're going to measure it in the Kelvin temperature scale. What you'll find out as you start to heat this ball up is that about the time it's 800 Kelvin, it's about the same color and brightness as the coils on your electric stove when they're running flat out. At about 2000 Kelvin, it's about the same brightness and the same color as a candle. At about 3200 Kelvin, it's about the same brightness and the same whiteness as production lights that are used in television, in film, and in theater. At 5600 Kelvin, this thing is bright and it is so perfectly white it matches the sun at noon on a clear day. And as it continues to get hotter, up around 9,000 Kelvin, it's clearly turning blue. It looks like the sky looks just after the sun's gone down, right? If you're looking up at the blue sky around dusk, that's about a 9,000 K color temperature. There are only two of these numbers that you really need to remember, at least for the purpose of the class. 3200 K is the color temperature of production lights, tungsten halogen lights, if you want to get technical on it. And 5600 K is the color temperature of the sun at noon on a clear day from the equator, if you want to get really specific. You'll find these referred to in a lot of cameras as daylight and interior, or inside. 3200 K, if you're shooting somewhere that has production lights, if you're shooting in a theater, if you're shooting in a television studio, if somebody has brought production lights to your set, probably you could work with the idea that this is a 3200 K light, and if you needed to use a preset, you could use that 3200 K preset. If you're shooting outside during the day, your color temperature is going to be somewhere in that 5600 K range. Now again, at noon, if it's clear and we're awfully close to the equator, it will be 5600 degrees. The earlier or later in the day you get, the more that shifts, right? As the sun is lower or lower in the sky, it goes through more atmosphere, more blue disappears, so the color temperature actually gets warmer. It'll drop down to 5,000, maybe even 4,500, just after sunrise or just before sunset. When the sun dips under the horizon, the only thing you get is that reflected blue from the sky, so the color temperature skyrockets. But anyway, remember these two numbers, 3200 K for indoor, 5600 K for the sun. You're going to see those again and again. You'll see it on pretty much every camera you pick up, and you'll see it on my tests. Now, white balance is the process of telling the camera what the color temperature is that you're shooting around. You have to do this right, or your footage will come out looking wrong. It'll either look blue, you're shooting in Smurf vision, or it'll look very warm, very orangey. It's pretty simple to do this. First of all, you need to make sure that the camera is set to manual white balance. Odds are excellent that the camera has an automatic white balance, and it probably will fight you. Some of your cameras might choose white balance, automatic white balance over manual. Make sure that you're set up to do it manually. Once you've accomplished that, you need to take a white object and you need to put it under the lights that you'll be shooting in. So I'm shooting an interview with Buzz Lightyear here. I gave him a white piece of paper to hold for me, and I made sure that the production lights I'm using were turned on. The next step is to zoom in on that white object. You want to fill the viewfinder as much as you can with only white. You don't want the camera to get confused by extra colors. Here I've got a little bit of his hand in there. There's some purple and some green. It's not ideal, but there's just a little bit of it. It shouldn't be too bad. The next step is, while you've got the camera pointed at that white object, press the button that says, "Take the white balance now." The camera should give you a little message that says something like automatic white okay, or white balance okay, or whatever, and it'll give you a number. Now you can see that I've taken a picture of the viewfinder here, and I've circled the display. The color temperature is 3000 K, and here's a little bit wider shot of that same image, just so you can see it in context there. So these are actually the fluorescent lights in my classroom that I'm shooting under. So they're not a solid color temperature. 3000 is kind of a meh number, but whatever. The camera is set appropriately, so I have every reason to believe that the color will look good. All right, so you need to remember to do this every time you go out shooting, and you need to remember to do this every time your lighting changes. So if, like me, you were shooting indoors, the lighting is not going to change. There are no windows in the room, right? So the lighting is constant. I can white balance once at the start of the day, and it will be fine all day long. I will not have to worry about it. If you're shooting somewhere that the color temperature of the light is changing, and this is particularly true if you're shooting outdoors or if you're shooting near windows during the daytime, the color temperature of the sun is not constant. Again, as it gets higher and higher into the sky, its color temperature rises, and as it gets closer to the horizon, its color temperature lowers. Clouds change things. When a cloud goes over the sun, the color temperature skyrockets. It gets very blue compared to regular daylight. So when you're shooting outside, you should white balance constantly. You should white balance every shot, or almost every shot. So that's all you need to know about color temperature and white balancing.